Well, good evening. It's a real pleasure and honour to be here tonight, and I've been enjoying the Santa Barbara weather and the environment of KITP for 2 weeks now. So I've seen, I think, the whole cycle from the bright sunshine through to the June gloom, which I reckon is a pretty challenging forecast problem, by the way. But you'll know more about that than I will. So tonight, if I can make this work? No? Okay. So I was asked to give a public lecture, and something in the spirit of the program that we're working on right now, and Baylor Fox Kemper over there is the prime organizer. And really what we're trying to do in the program is understand some of the interfaces, the physical interfaces in the climate system. So we know that the increases in carbon dioxide are warming the atmosphere, warming the oceans, but the transport of heat between the atmosphere and oceans is controlled by some really thin layers, just a kilometre or two thick either side of those interfaces. So that's what we've been studying in this program. And what I'd like to do today is just give you a slightly broader context on climate science and a really pivotal event for the climate science. The pointer doesn't work. I guess the battery's gone flat. Too many rehearsals earlier, clearly. Let me go back to the old technology. I thought this was just for hand-to-hand combat for the questions, but evidently not. So a really sort of pivotal moment, I think, in climate science, from a climate scientist perspective, but also as a citizen of the world, was this Paris Agreement. So I'd like to just start by saying a few words about what that involved, and then how that's led us to rethink the science that we're going to do. And I do apologise, the projector's not reproducing this figure terribly well. So arguably, before this Paris Agreement, so this was one of the conference of the parties that takes place every year, rotates around the world, and 196 countries go to those negotiations and negotiate what the world might do to combat the changing climate due to emissions of greenhouse gases. Before Paris, I think climate science had two really straightforward questions to answer, at least they're straightforward to state. And the first question was, is the world warming? And that's a straight observational question. We need measurements going over a sufficiently long period of time to see if we can detect warming. And we see warming in the global mean temperature, in shrinking sea ice, in rising sea levels. There are hundreds, literally, of measures of a warming climate. So this led the several hundred climate scientists who get together every 7 years to produce the Intergovernmental Panel on Climate Change's synthesis of our understanding, several thousand scientists to agree that warming was overwhelming. Okay, so just imagine trying to get several thousand scientists to agree on that. And Baylor's going to be participating in the next IPCC report, so that's the challenge you need to live up to. So first question, is the world warming? And there's really overwhelming evidence for that. Thank you very much. Second question for climate science then, before Paris, was given that warming, is that warming due to human emissions of carbon dioxide and so on? Is it human-induced climate change? And again, the last IPCC, the Intergovernmental Panel on Climate Change report, concluded that it's very likely, and this is calibrated language, meaning a greater than 95% chance on expert judgment, that the majority of warming seen over the latter half of the 20th century is due to increased carbon dioxide and other trace gases in the atmosphere. So this was the body of science that the political negotiators had at their fingertips when they went to Paris in December in 2015. So do you remember what you were doing on the 12th of December 2015? Because I think it should really be one of those days where we try and figure out what we were doing. So I was in a windy suburb in the outskirts of Paris with a couple of thousand other people, all hunkering down, trying to, in my case, help the British delegation take the evidence to the negotiations, and then the negotiating parties actually understand what could be done. So the scientific consensus is built before the meeting, and then there can't be any argument amongst the negotiators and the political agents about the political evidence. That's a done deal. So with that evidence, and part of it's shown here, so again, apologies, it's not come out terribly well. What you're seeing here between the pale and the dark blues is the temperature record, global average temperature, going from 1850 on the left through to present day on the right-hand side. And the way we calculate this is through thousands of measurements of screen level temperature, to use that term here, these white boxes that sit about that high off the ground and measure temperature. So we average those and we do various data processing and correction for cities encroaching on them, etc., etc. And we get this curve, and we can see, particularly in the latter half of the 20th century, quite a marked warming up here. There's warming earlier in the century, and then the Second World War period is here. And there's something of a dip or a slowdown in the warming here from the 50s through into the very early 1970s, and that's likely due to pollution in the atmosphere. Effectively, small aerosol particles, so small particles emitted through burning, reflecting sunlight directly back into space. They're acting like little mirrors in the sky, reducing the amount of heat coming into the climate system. So that has a cooling effect. And then as we cleaned out the technology, the warming due to the carbon dioxide takes off, and that's what we're seeing in the latter half here. So as a result of this and other evidence, Paris really ratified the pledge to keep global average temperature rise well below 2 degrees C. So this is an expert judgment, and 2 degrees is reckoned to be somewhere where the damage won't be so big, and yet it's possibly still achievable. From a climate scientist perspective, the real surprise was that the negotiators came out with this aspiration to limit global average temperature rise to 1.5 degrees C. And we hadn't heard this number before. And it's a surprise because you can see in the last 3 years of the observational record, we've actually peaked above 1 degree above pre-industrial already, right? So we're at 1 to 1.1 degree above pre-industrial already. So 1.5 is pretty close, right? So the first thing that this is demanding of the science is a degree of accuracy that we never had to confront before. Before we were saying, is it warming? Now we need to say, keep the temperature below 1.5. That's a whole different ball game. So, okay, so that was the aspiration. The measures that were written down into the agreement broadly here around emissions. So a long-term aim to reduce emissions to net zero emissions. Carbon dioxide stays in the atmosphere for roughly 100 years. So roughly what we emit now will stay around for long enough for this to just keep accumulating. And as the carbon dioxide concentration increases, so the warming increases, so the temperature will rise. So if we want to stabilize the temperature, it's zero net emissions of carbon dioxide. So if there's one thing you take from this lecture, I'd like that to be it. For every ton of carbon dioxide we emit, we're going to have to suck it back out of the atmosphere somehow. And whilst there are some technologies to do that, they're very experimental. So zero net emissions by 2050, that's a very bold objective, but if we're going to stabilize the climate, we have to do that. Aim for greenhouse gas emissions to peak as soon as possible. So many of the scenarios that keep us below 2 degrees imply peaking in emissions in the early 2020s. When I started working in this area 20 years ago, the 2020s seemed an impossible distance away, but we're 2018 now, right? So peak emissions in the next 5 years to have a good chance of reaching 2 degrees is the current estimate. And then, notwithstanding the level of ambition of those, an increasing ambition over time. So we'll see what that means. Then there were a range of financial instruments and reviews. So there's some interesting science here. So reviews, so a global stocktake to assess the progress every 5 years. So if we're going to go to zero net emissions, and part of the Paris Agreement was that every country made a pledge for how it would reduce its emissions over time. there needs to be an accounting system that will check that countries are honouring those pledges. And one of the ways we can do that, we can measure carbon dioxide from space, from satellites actually in the atmosphere, and using inversion modelling from those measurements of the carbon dioxide, we can make some inferences about where that carbon dioxide has come from to get some objective measures about national emissions. But that's in an early state, I would say, but clearly a technology we need to develop. Okay, the financial parts were the real difficult elements, I think, of the Paris Agreement. I was not, of course, involved in those at all. So climate finance to support adaptation to a changing climate in developing countries. And then loss and damage. This is a particularly controversial topic. Loss and damage associated with adverse impacts. So it was mainly the low island states the Pacific states who introduced the 1.5 degree, and of course they're very susceptible to sea level rise. So the concept here is that if sea level rise destroys their country, then someone is going to have to pay for that loss and damage. So there's a whole question there about how do we attribute that sea level rise to that location to climate change, even before we get to the question of who pays. So there's an attribution question there which is going to demand science. And then we know that if we went to zero net emissions of carbon dioxide right now, the climate will continue to warm for 20 or 30 years. So we are committed to a climate that's warmer than we've got now, and over the last 50 years we've seen some warming. Okay, so you can see some new scientific themes building on the relatively straightforward questions of is the climate warming, and if it is it due to emissions of carbon dioxide?
A bit louder, sir.
Oh, I'm sorry. Our technical expert is joining us at the back. Is that any better?
No.
Okay. Okay. Okay, how's that? Okay, good. Do shout back if I go quiet again. Okay, final piece of context. So 2015 wasn't actually just the Paris Agreement. This was the moment when the agreement was adopted by the community. So also in 2015, the United Nations launched a new set of new framework to address disaster risk reduction. So this is things like flooding events or large landslides or underwater landslides that lead to tsunamis. And what the United Nations were aiming to do, or are aiming to do, is to set up more coordinated research internationally that can lead to early warning of these kind of systems. And of course, many of these disasters are carried by weather events or climate events. And so how those weather and climate events change in character under a warming climate is really at the root of that. And so one of the elements we need to do now in the science, and I'll come back to that point. It's fading again, isn't it? Okay. The United Nations in 2015 also launched the new Sustainable Development Goals. So this was an update of the Millennium Development Goals. And there are 17 Sustainable Development Goals. So I've presented this slide before, and I ask the audience every time, why are there 17 development goals? And this is in the hope that someone in the audience knows. Other than 17 being a prime number, I have no idea why. It seems an awful lot. So Sustainable Development Goal 13 is on climate action, so that's the climate problem that we're talking about directly today. 14 is life below water. So if we think about the seas, one of the impacts of climate change is to acidify the oceans. So there's a climate change dimension there. There's Sustainable Development Goal 6 is around clean water and sanitation. So we know that rainfall patterns will change under a changing climate. So availability of water is going to be an issue, particularly in areas that are already water stressed. So you can see that, again, weather and climate sits under quite a lot of this. And in fact, even things like gender equality, there's evidence that in some cultures, when droughts come about, it's the women who often have to go and collect the water, and that can pull young women out of education. So it's a very indirect and not the primary driver, but it does emphasize the fact that weather and climate sits under all of these. So 2015 really, for my community, I think, was a major year. Okay, so that's all kind of background context. So what does this mean for the science we need to be doing right now? And I'll mention 4 elements. So the first is getting better monitoring systems to understand what's happening right now and how the risks associated with weather and climate events is changing is a big deal, and capitalizing on satellite data is important there. Secondly, very directly related to Paris, you'll recall that there's a pledge to remain below 2 degrees and an ambition to remain below 1.5. Well, the question is, what emissions pathways give us a chance of achieving that? And there's some very delicate science involved in that I want to give you a flavour of. And then moving on to the weather systems side, so this is where my expertise comes in. We talk a lot about climate, but actually it's the weather events that do the damage, right? And understanding how the character of those weather events will change as the climate changes is a really hard problem, and not one that's been heavily studied to date, actually. And then the impacts of these weather events I'll touch on briefly towards the end. Okay, so monitoring. So I already showed this. This is the data showing the global mean temperature. And there are really 3 data sources which tend to be used for this kind of study. So one is ours at the Met Office within the Hadley Centre. The second is a NOAA data set, and the third is a NASA data set. The actual observations that sit under these are broadly similar, but there are some methodological differences. For example, there's very few observations over the Arctic or the Antarctic, for obvious reasons. And so the way that we spread the observations or use them to represent a larger area, there are some differences in detail there. You'll see that these 3 observational data sets give pretty much the same answer. There are some variations. And in fact, let's see, it would be about 7 or 8 years ago, we had a newspaper story that some emails had been broken into in one of the universities in the UK. And there were allegations about the propriety of how these data sets were put together. So number 1, these are independent analyses and they agree pretty well. Number 2, as a result of this email hacking scandal, a group at Berkeley decided they'd start from bottom up and do it all again, and the story is almost indistinguishable. I don't know if there are any historians in the house this evening, as they say. We're using as a baseline, I keep talking about 1.5 degrees and 2 degrees, and that's above a pre-industrial baseline climate, which is kind of taken to be not influenced by emissions of carbon dioxide. So you might be asking, well, how do we compute or how do we measure that baseline? And the answer is that these purple lines give an estimate of the uncertainty on this measurement of the global mean temperature. And you'll see that in present day, when we've got lots of observations, that range is rather narrow, but it increases as we go back in time because the quality of the data reduces and the number of observations reduces. And in fact, going back prior to 1850, the community tend not to do in this kind of way because the density drops off. So as a pragmatic choice, we take 1850 to 1900 as our measure of pre-industrial. And as I said, I don't know how many historians there are in the room, but a friend of mine's a historian, and I think he'd argue that the Industrial Revolution was pretty much in full swing by the 1850. But it's just a pragmatic...
1750.
Right. So this is a pragmatic judgment, okay? And it's the best we can do with the observations we've got, but going back sufficiently far. Okay, and I've already talked about the dip here with the aerosols and then the rapid increase to over 1 degree. So I just thought I'd show you this animation here. There's been, at least in the UK, quite a bit of interest in tools to visualize data like this, and I thought I'd show you one example that we just produced recently. So this is Colin Morris at the Met Office produced this, and he calls it the rising tide of temperatures. So here's that 20th century record of global mean temperature, and what we're doing is sweeping up from the lowest temperature in the record, just increasing the temperature to the highest, and then we're picking out the year in which that temperature occurred and then the month. So the blue indicates this cooler temperatures, global temperatures, and they're tending to happen earlier in the record, as you'd expect. As we go further through, the warmer temperatures, of course, are more in more recent times, but I wondered if any of the eagle-eye... blast. Okay. No, I keep mishitting this. Okay, we'll let it run through one more time. No, total failure. I'm going to try and just pause it on the end. Okay. So, you know that, well, I don't know about California. Where I live in the UK, the temperature is warmer in the summer than it is in the winter, so there's a big annual cycle. I hear here it's pretty flat, right? It's like a tiny... But there's you see very little annual cycle in this temperature, and this is for the obvious reason that this is a global average, right? So you average the winter and the summer together. However, if you look really carefully, the very warmest temperatures, which are over 1.2, 1.4 degree, just for a month, the months can be higher than the annual mean, which we were showing earlier, do tend to occur in the winter months. Any ideas why that might be?
You're talking about the northern hemisphere?
This is global average.
Because you've got 3 million mile difference in distance from the sun to the other between
influence of Antarctica.
winter weather.
Okay, we've got some great ideas here. So it is regional variations. There's more land in the northern hemisphere than the south. But I think in this particular case, and I can't quite reach, this was, okay, this is really not working. What a pro, as people keep telling me. What is happening is that this was an El Nino period. So an El Nino is a time when the Pacific waters become very warm, and it's a sufficiently large area to actually elevate global mean temperatures. And the El Nino runs roughly through from, January or so through to the following year, but not during the summer months. So that's why we're seeing the very hot months right here. Okay, so, but my message is monitoring the risks, and this is mainly land-based data actually, rather than satellite data, so moving to a satellite system is... Okay, so let me say something about the carbon budgets now. And just to do this, I'm going to just pull up this website. Is that going to work? Okay, I'll use the YouTube version. Okay, so try and ignore what's happening on the right here. That's my son's viewing history, I think. So what we're seeing here is what happens to the carbon dioxide that's emitted into the atmosphere. So again, if I can try and pause that. Okay, good. So the emissions of carbon dioxide are shown up here on the vertical axis, and the emission, they're in gigatons of carbon per year. So this is a subject with big numbers and small numbers all mashed up together. A gigaton of carbon is a lot of carbon. I don't quite know how to visualize that. And the emissions come from this wedge from fossil fuels and cement, but mainly fossil fuel burning. So you can see that makes up a large fraction, very large fraction of the emissions. There's also an emission due to land use change. So this is things like clearing of forests and then burning of the biomass. And biomass is carbon. As you burn it, it releases the carbon back into the atmosphere. So this is making up order 10% of the total emissions at the moment. You can see, by the way, the emissions are showing no sign of decreasing. In fact, after some dips, they're going up more. This lower set illustrates where the carbon goes. So not all of that carbon dioxide remains in the atmosphere. So the pale blue wedge is the part that does remain in the atmosphere, and it's about half of the total emissions at the moment. Of the remaining half, about half goes into land-based vegetation. So this is the plants growing, taking in carbon dioxide and fixing it into carbon. And the remaining roughly half, maybe a little less, is taken up by the oceans. So one of the topics we've been studying here, actually, taken up by the oceans, causing plankton to grow, the sort of basis of the ocean food web. So at the moment, about half of our emissions remain in the atmosphere and lead to warming of the climate. So, big question, will it remain a half or will it change? And you'll notice that in this more recent period, since about 1990, there's a big wiggle between this dark blue wedge, the land-based carbon, and the light blue wedge, which is the atmospheric constituent. There's a bit of wiggle between the ocean, but it's much less so. So the fraction taken up by the ocean is roughly constant. There's less variation. Again, the reason for this is that there are some years when there's much more vegetation grows than others. And actually El Nino, again, can be a very big driver of this. It can drive increased rainfall, particularly over the Amazon, and many plant growth is limited by water availability, so more rain means more carbon. So particularly on the land-based carbon, there are some real questions about what will happen to this fraction over time, and hence what will happen to that. And I'll come back to that in just a few moments. Okay. So a tool that was developed in the last IPCC report, the Intergovernmental Panel on Climate Change report, which went into the Paris negotiations, was this figure here. And this shows the total amount of carbon dioxide that has been emitted into the atmosphere over the course since the Industrial Revolution. So it's an accumulated mass, gigatons of carbon since 1870. And then the vertical axis shows the global mean temperature anomaly relative to some baseline, this pre-industrial baseline. And it shows roughly a straight line. Actually, the fact that it's roughly a straight line is kind of an accident. There are all sorts of logarithms and exponentials going on here which kind of cancel. So it wasn't at all obvious that it would be a straight line. But for policy guys, this is really helpful because it introduces the concept of a budget. So my numbers, I apologize, are a little bit out of date. As of 2015, we've emitted an accumulation of about 555 gigatons of carbon into the atmosphere, so this dotted line. And this gets us to somewhere between 1 and 1.5 degrees above pre-industrial, right? Because we're in this plume. If we want to stay below 2 degrees, then we need to stay within this wedge here. So if we take some central estimate and read it down, then good estimate to give us a 50% chance is we've got about another 400 gigatons left to burn. So we're over halfway to 2 degrees, this is, let alone 1.5. And on current rates of emission, which you saw were going up, we've got maybe 15, 20 years left before we achieve that. So that's the urgency. The science is that there's a huge spread here. So this envelope is a sort of expert judgment based on what we know and the quality of the models and uncertainties in the models. But this is a factor of 2 or 3. And as I mentioned before, if Paris has done nothing else, it's to drive an accuracy that we've never had to face before. But this really matters now. So how can we narrow that range of uncertainty? And I have an example in the next slide, which will give one route to that, which is kind of a neat trick. The other thing that can happen here is, are there things missing? These are the models here, and this is some expert judgment around that. Are there any things, what are we missing in the models that could lead to biases in that estimate? And there are at least two examples. So one is, I talked in the previous slide about vegetation on the land taking out carbon dioxide and fixing it into carbon. The gardeners in the room will know that a limitation on plant growth can be nitrogen. So the models, the simulation tools that we use to build these estimates do not have nitrogen limitation at the moment. The next generation will. That will tend to reduce the amount of carbon that plants are taking up in the models, and will tend to steepen this line and give us less fossil fuel burning before we reach the 2 degrees. Another bias potentially is melting of permafrost. So in high latitudes, Siberia, northern Canada, there are huge volumes of carbon locked in permafrost in the ground. Once that melts with a warming climate, that carbon can then be released back. Again, this is a bias that will reduce the allowable carbon we can burn. So it's a great tool, but it does expose the need for quantification and accuracy that maybe we haven't had to confront yet, and there's a huge effort to reduce that. Now, I was told by Mark and Lars that you're an audience who do like real physics, so that's what you're going to get on this slide. So I thought I'd just give you a hint at some of the neat tricks that are being developed now to try and nail down that uncertainty on that previous plot. So there's a topic called emergent constraints. So what this formula is about the change in the carbon stored in the tropics on the land, so the Amazon, the African rainforest. And that change can come about through broadly two processes. One is, as the carbon dioxide concentration increases, this stimulates more growth. So it's possible to do experiments in greenhouses and just pump in more carbon dioxide. Sure enough, the plants grow. It's a CO2 fertilization. And the second element is a long-term climate change. As the climate warms, that will increase the store of carbon. This number is really poorly constrained in the models, and the models have a big range. And this number is the one that tells us if we warm the climate by 2 degrees, the additional amount of storage of carbon in these forests, so the amount the forests are going to draw carbon out of the atmosphere. So a piece of work led by Peter Cox, jointly University of Exeter and the Met Office. Peter noticed that if we look at the interannual fluctuations of carbon dioxide concentration in the atmosphere, they do vary by a small amount. So some years there's a higher concentration, some years it's slightly lower. And again, El Nino is a big factor in this. In El Nino years, there's more rainfall in these tropical regions, there's more growth, and that tends to remove more carbon from the atmosphere. So we think that interannual variation in carbon dioxide concentration is because of variations in the growth of the plants, and so can tell us about this long-term trend. So sure enough, if you plot the models, the value of their sensitivity to varying CO2 year by year to their long-term change, you get this wonderful straight line. So the models have very different values, but they all sit on a straight line. What we can then do is look at measurements of how carbon dioxide concentration varies year to year, and then we can read off what the long-term change could be. So it's kind of a neat way of using something observable about short-term fluctuations in the climate system to tell us something about the long-term fluctuation. So this whole topic of emergent constraints is a really big topic in climate science at the moment. Is this a question?
Well, I've just got a question. We can't predict the frequency of El Nino.
Right.
Maybe once every 5 years, maybe not even
Yeah.
that. So relying on that as a mechanism.
So what we've done is we've looked at the measured carbon dioxide variation. Some of that variation has come from El Nino, but it's the range of concentrations that we're interested in, not the frequency with which we get that change. So it's the difference between the high concentration years and the low concentration years, and that's effectively what's plotted on this axis, and that gives us a reading of that, if that helps clarify that point. So hunting for these things has become a real industry, and it's helping us to narrow some of these uncertainties. Again, to give you a kind of physics angle on that, the perverse byproduct of this approach is what we want are lots of models, simulation tools, that have very different behaviors. We don't want one model that the world thinks, or the world scientific community thinks, is the right model, because that would just that would just give us one point. We need lots of models with a big dynamic range and some observable to give us this correlation which we can then read off. So a diversity of models with a diversity of behaviors. I think in physics, I don't hear people talk about this too often. We want lots of models giving us lots of different answers, not one right one. Okay, so briefly, I'll speak for another 5 minutes or so and then we'll move into questions, but I'll just say something about the weather events and how we're tackling those. So in 2014 winter, we had a real stinker of a winter in Britain, and we broke records for the southeast of England rainfall amount. So it doesn't rain all the time in England, but my gosh, for that winter it really felt like it rained all the time. So we got, over the southeast, so including London and so on, more than 200 millimetres of rainfall during just January, in fact. So that's a lot for us. Typical value, it's more than double the typical value, which would be something like 100. If you're in the tropics, this is nothing to boast about, but for us it's a big deal. So what the black line here, from 1980 through to present day, is showing those rainfall amounts for southeast England, and you can see 2014 sticking out. So immediately this happened, the phone to the Met Office rings. Should we have expected this? Is it climate change? What are we going to do? And in fact, it prompted a review of the flood defences in the UK as a result of this. So what we can do, of course, is to look at the previous observations in rainfall, and that's this black line here, and you can see the previous range was 25 millimetres going up to just over 150. So on that measure, it was an extreme event. We could go back further, but then we're kind of sampling from a climate changing record, so you can't do that. So we reckon that only going back 30 years is a sensible thing to do if you want to miss out any climate change signal here. So in terms of the observations, that's been the range, and then 2014 was right out here. It looks like a terrible outlier. The tools we have for simulating the weather, and they're the basis of weather forecasting models as well, are so good now that what we thought we'd do was run synthetic years on present-day climate, just run simulations of synthetic Januaries to make a data set of Januaries that could have happened but maybe haven't yet happened, and put these observations into that context. So the red lines here are examples of those time series of these synthetic January or winter rainfall over southeast England, and they bounce around, and sure enough we do see other events that were as extreme as that. This is not climate change, this is just what comes out of a model for present day climate.
Dr. Belcher,
Yeah.
100 millimeters is only 6 inches of rain.
Yeah. Yeah, this is correct.
6 inches of rain, that's all?
Yeah, in January, 1 month.
In a month?
Yeah. Yeah. But you're right. For many citizens of the world, this is nothing to write home about. But for, in England, if it snows half an inch, the country shuts down. If it rains 12 inches, then there's a state of national emergency. I thought what you were going to ask is, surely you're not going to base government policy on some crummy simulation. So how did you test that? So we had 3 tests. One was to look at the statistics of this, the mean and the variance and the skewness. And we looked at probability density functions and all those kind of fancy measures looked okay. But the third measure we used was that in the Met Office we have a big research program, but we're also the National Met Service, so we've got real weather forecasters. So we could pick out the synoptic charts for this really wet winter here that came out of the computer, and we could shuffle that up with the one that actually occurred in 2014 and some other simulated ones, and we could ask the forecasters if they could pick out the simulations from the actuals, and they couldn't. So, you know, there's another kind of human dimension to the check. I wouldn't stake the entire reputation of the Hadley Centre on this, but it's kind of a nice check. So with these simulations, we then have 1,000 years of possible January rainfalls, and that's what the statistics of these look like. So the range is a bit tighter than the observations, but you'd expect that because it's a much more filled out set of possibilities. But more important, the extremes are broader, not surprisingly, than we've experienced in nature in the last 30 years. And in particular, in this particular case, we had 3 simulated winters that look wetter than that one, but only 3. So the conclusion of this is that 2014, it was a stinker, it was really wet, but it is within the bounds of present-day climate. And so that's kind of important, because we can then look at other regions of the UK, which is what this figure does, in different months. So this actually is southeast England, but for different months. And the blue again is the observations, and the red is showing these 1,000 years of imagined. And where you're seeing the red dots is where the simulations are saying we could have a wetter month there than we've actually experienced to date. And the conclusion of this is that on average there's a 10% risk of an unprecedented rainfall in winter in any one region of the UK. So every 10 years we're going to break a record. So don't set your flood defences by what you've seen so far, because there's 1 in 10 chance you're going to fail. So that's kind of a big deal. And as I say, this fed into a review of UK flood defences that's built a bit more resilience. The final comment on this is that when we started this technique, we described these as black swan events. So a black swan, right, is you all know what a white swan is, but you haven't yet seen a black swan, although you think it might be out there. And we have a big collaboration with Brazil, largely because of the tropical rainforest there and the work I was talking about earlier. And I presented this and I talked about black swans, and they were very appreciative of the information and thought that this technique might be very helpful for Brazil as well. But at the end someone said, but I don't understand why you call this black swan. You know, look out of the window. There are black swans everywhere in Brazil. It's not a big deal. Okay. So you can imagine that getting this kind of information into future projections is going to tell us the character of future weather events. And we're just building the next set of climate projections for the UK, and we'll launch those in about 6 months' time that will do that. But I won't dwell on that for the time being. Okay, I'm conscious of time, so I think I'm just going to have one final slide before I sum up. So we've begun to characterize there the weather events and what's possible and what might not be possible and what might be possible in the future. So we can use this kind of technique to look at impacts on food production in this case. So we had a study on maize production. So a huge fraction, I think something like 90% of maize production is basically two baskets in the northern US and then in China. So first question is, how often might you expect failures due to drought in one of those bread baskets or maize baskets? But then, given that we know weather systems across the world are connected, what's the possibility of them both failing, a dual failure? And you can see with these long simulations and these 1,000 years of simulations, we can really get access to these rare events. You'll be probably not surprised, but relieved to know that the chance of both breadbaskets failing looks extremely low according to this technology, and perhaps that's part of a human evolutionary process. But my point here is that using these techniques on the weather information in a changing climate, I think, is really unlocking the possibility to study the impacts of climate change in a way that we couldn't really do before. Okay, so to end, can I invite you to go back to your diary, 12th of December 2015. It's a start, the Paris Agreement. It's the first time that 196 countries signed up to do something specific to address climate change. And I think as of today, 176 nations have actually signed up to the agreement and the commitments. So it's a real day worth celebrating, but as a scientist, it's really changed my job. And I think for all the participants here, we now have some really hard problems that we need to work out. Now we've solved the relatively easy ones. And with that, I'll finish. Thank you very much.
Yes.
Well, I guess a major political argument is some people are saying that it isn't us, that there are other natural factors that have happened periodically over the many years. Could you speak to that?
Yep.
Clarify that argument for us, perhaps.
Well, so carbon dioxide concentrations are unprecedented in geological time that we can explore. I forget the numbers, but it's hundreds of thousands of years. I'm looking at Baylor, that he's nodding. 300,000. 800,000, thank you. So fact number one, observation. There's no model in that at all. The rate of temperature rise is really quite rapid at the moment. I think the third element, perhaps I didn't talk about this, the physics of how carbon dioxide in the atmosphere warms the planet is straightforward radiation physics, which Arrhenius knew about in the 19th century. So we've got simple physics for why carbon dioxide should warm the planet. We've got observations of carbon dioxide going up and of temperature going up. Furthermore, we know from modelling studies that the poles will tend to warm more than the equatorial regions. The land tends to warm more than the surface of the oceans. We see that in observations too. So you can see it's this accumulation of evidence from multiple sources that gives us confidence to say, firstly, that the evidence for warming is overwhelming, and it's very likely due to emissions of carbon dioxide.
But it's our fault.
Well,
That's the big question, is whose fault is it? Is it our fault, or is it just a natural event? And that's what the argument is.
Well, so the carbon dioxide in the atmosphere, I don't know the details of this, but it's possible by using isotope ratios to be certain this is due to fossil fuel burning. Okay? So that increase in carbon dioxide, you cannot argue it's fossil fuel burning.
You do the math on the fuel that was burned, the carbon dioxide, and how much it raises, and voila, that's the temperature.
Yeah.
Okay.
Yeah. So that's absolutely nailed. And then, as I say, the other evidence is multiple sources of evidence that carbon dioxide then gives the warming that we observe, not just in global measures, but in spatial patterns as well. Okay?
Thank you.
Good.
What about the effects of the unpredictable release of methane from the melting ice?
I think your question answers itself, unpredictable. So, okay, I'll attempt a slightly more nuanced answer, but it won't be much more nuanced. So we can estimate when permafrost could melt. Really, this topic is constrained by observations of the structure of the permafrost and the vertical structure, because basically it's a diffusion problem to get the heat down to the levels in the ground where the ice matrix sits and how you need to melt that. So you need to know the structure of that vertical structure, and we don't have a great handle actually on the reservoir that sat there. So these are two major limiting factors. There are estimates, I don't have them off my top of my head, but it's a non-trivial contribution in terms of those gigatons of carbon I was talking about earlier. Yeah, okay.
Could you comment on the theory that a more subtle phenomenon has been going on for order of 10,000 years, where anthropogenic release of carbon has gone hand in hand with the development of agriculture and the burning of forests?
So let me see if I can.
What was the question? Could the speaker comment on that theory that we've benefited from? Oh, that we've benefited from a warming of the atmosphere over the last 10,000 years, and this has enabled the agricultural revolution to succeed.
So my expertise is in physical climate science, so I can't address your question very directly.
No, but just what's the history of temperatures in the last 10,000 years?
Right. So, since the last ice age, the temperature has been reasonably stable until post-industrial times. Clearly there are long time variations in the temperature, so there was a little ice age in the Middle Ages, and the reasons for that have been hotly debated. It's probably something to do with solar influences. It's probably just a European phenomenon. There's no evidence that that occurred in other parts of the world. So it's not a global ice age, it's just a local deviation. So I think the evidence is that global mean temperature has been reasonably stable since the last ice age. The relationship between this and the development of humans, I'm not sure I'm the right person to comment upon. Okay.
With that chart up there, you mentioned when it was up before, you mentioned a couple of technologies to extract carbon dioxide that aren't natural.
Right. So these are all pretty speculative. So one idea is to literally take the combustion products from a power station and pump that underground into the region where we maybe got the oil from in the first place. So this is called carbon capture and sequestration. This has been tested in, I'm going to get the name wrong, an oil field, I think in the North Sea, on relatively small scales. It may work. There's a lot of investigations going on if there's cracks in the rocks, how easily will it be to escape? If it did escape, could we detect it? That kind of thing. So scaling up that technology is unproven. The other area which some of the scenarios for the future talk a lot about is biofuels. So we grow crops in order to burn them to generate energy, and then we take the carbon, so that's actually a negative carbon energy source then. The issue then is the land. Where do you grow this biofuel? And are you replacing food growth to grow biofuel? So there's some massive tensions there. So some of the scenarios that would keep us below 2 degrees, and certainly 1.5, have very aggressive deployment of these technologies, which, as I say, are largely unproven at the moment. And so that's a major challenge, I think, for achieving these targets. Yeah. Please.
I think there's a Malthusian dilemma here too.
Okay.
If we believe that humans are causing this, human population is going up exponentially, and product is standard of living, and the damage is the product of the two. So it would seem that the steps you have to take are either reduction of population or the reduction of standard of living, or you could just let it go and it's going to crash, right? Do you agree with that?
Well, within that question, there's a whole bunch of ethical and moral dilemmas which I think it would be unwise of me to get too involved in. I mean, we will all have an individual reaction to that, and because the nature of climate change is a global issue, individual nations will react in different ways, which could be behind your question. So different countries need to figure out how to address it in different ways. There are some nice tools online to understand and just audit our own carbon footprints. And there are several things that kind of stand out. One is air travel, so Kavli Institute, take note. The slow boat back to England, it's looking like a better option. Yeah, thank you. Eating meat, so one of the interesting calculations that we haven't completed yet is, with a growing population who need so many calories a day to have a healthy life, what's the climate change commitment? Because agriculture is a big contributor to emissions, particularly of non-carbon dioxide. What's the climate commitment to feeding the world? And I don't know the answer to that at the moment, but that's where a physical scientist, I think, can begin to contribute to the complex debate that you've raised. Yeah.
Can you say something about the effects of U.S. policy on the chances of reaching the goals, including the shutting down of NASA data collection?
Okay. So that's a tough question, and as a British citizen, it would be unwise of me to speculate on foreign policy. Right. So the US scientific community is enormously important in the global climate science community. And so any effects on that would be a real shame for the subject, I think, and would kind of stall progress in a way that no one will want to see. You asked about individual policies and the achievement of the Paris goals. As part of the Paris goals, each country was asked to make a pledge for how it would reduce its emissions. And in the negotiations, that was the breakthrough. Rather than imposing reductions on countries, countries were asked to bring them to the table. What we observe, I think, at the moment is, at least in the UK, it's a combination of national government, local government, but also industries acting independently, but in the right direction is what's causing our emissions to reduce. So I would hope that kind of would follow through to the US as well. I'm sorry. The data collection. Oh, I'm sorry, yeah. So, I showed, for example, the global mean temperature data. Two of those data sets are US data sets, so there'd be a loss to the community if those were shut down, yeah. Weather forecasts use observations too. So I think we all want a weather forecast, and in order to start a weather forecast, we need measurements of what the atmosphere is doing right now. And when collated into long data series, they turn into climate data sets. But the primary use of these data is to make weather forecasts.
That kind of leads into another question I have, which is, how do you expect the use of satellites to transform your field? I mean, I could see lots more data points, but beyond that, like the types of data and when you can collect it and the way that you can coordinate, I'm curious.
Yeah, no, it's a great question, and I'm fairly certain I will only give a partial answer because there's many creative minds thinking about this problem. One is composition of the atmosphere. So some of the new channels are able to give vertically resolved understanding of constituents in the atmosphere. And so given that climate change is driven by effectively pollutants in the atmosphere, that will be one thing we'll be able to see. I talked about the carbon cycle and land-based vegetation. So some of these, while the traditional kind of weather variables have been measured quite some time, even with satellites, some of these new aspects of the climate system, like the terrestrial carbon and the plant growth, can be sensed from space now. There's a mission actually coordinated out of the UK, which is measuring the thickness of ice in the Arctic. So previously, the records go back to the 1980s of the area of ice coverage, and we've seen that shrink. But what we really want to know is the thickness and the area to give us the volume. And we also suspect that as the ice thins, it's more susceptible to breaking up, so the area also reduces. So there's a great cryosat which is able to measure the altitude of the ice, and from that you can back out the thickness, as some examples.
Thank you. I suggest that we continue the discussion at the refreshments outside.
Great idea. Okay, thank you.